Good morning, boys and girls, and welcome back. Today we'll be talking about derivatives and introducing them to you. We're going to start with our discussion of the secant line. And I remember from back in the beginning of our last unit on limits, the secant line, if this is a graph of time and distance, okay, that secant line would represent the average velocity, we said, because it's your change in distance over the change in time. Or if it's any other graph, it's just we said it's your average rate of change. You want to know that the slope of the secant line, and I think I forgot to say slope earlier, but the slope of the secant line is the average rate of change. Okay? Very important. And then we said if you were to take the, this secant line and you were to move points closer and closer together, kind of like this, that those slopes then become a pretty darn good approximation for the slope of the, here we go, slope of the tangent line right there. Okay. All right, so we talked about how those slopes become a good approximation, but our question was, how can we find exactly what it is, or actually what the slope of the tangent line is? So that's what we're going to kind of start to work on today a little bit. Let me refresh. Okay, so I kind of went back a little bit, and we're looking just at our secant line now. We have our function f of x, all right? And we're looking at the 2 points. One point, the x-coordinate is at a, and then we're calling this other point at some other x that's beyond a, where x is greater than a. And so that would give me the 2 points here on our secant line of x, comma f of x, and a, comma f of a. Okay? And so if I wanted to find the slope of the secant line, I could just do y2 minus y1 over x2 minus x1. And so that would be like f of x minus f of a over x minus a would give me the slope of the secant line. Okay? Just using our slope formula. All right, so if I wanted to use this to find the slope of the tangent line, what we said we're going to do is we're going to try to move this second point closer to the first point. Right? So the slope of the tangent line, then, I maybe could say is, I'm going to look at the limit as x approaches a, as I bring this x-coordinate in closer to a of these slopes. Not enough room. Let me erase here. This would be the slope of the tangent line. Okay? F of x minus f of a over x minus a, the limit as x approaches a. If we just take this, this x-coordinate, and we're moving it closer, as I move this, closer, 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 that's going to help me to approximate the slope of this tangent line right here. All right? So, okay, to sum up what we just talked about, your average rate of change is equal to the slope of the secant line, which is f of x minus f of a all over x minus a. Sorry, I just saw that little typo there. F of x minus f of a all over x minus a. The instantaneous rate of change is the slope of the tangent line, and that is the limit as x approaches a of f of x minus f of a over x minus a. Okay? So, slope of the tangent line, slope of the secant line is just between 2 points. The slope of the tangent line is as I move that second point closer to the first. So I'm taking the limit as x approaches a of the slope of the secant line. All right? That is our first definition of the slope of a tangent line. Okay? Now we're going to cover another definition of the slope of a tangent line. Okay, here's another way to look at this same scenario, the same situation. Okay? Just defining things a little bit differently. Instead of starting at a last time and x were our 2 points, now I'm going to say x is where I'm starting. Okay, that is my starting point. We're going to try to find the tangent line. And then I'm just going to go some distance h. Some distance h down the way. And so my next x-coordinate would be at x plus h. If I had that, I could write the 2 points x comma f of x would be the point where the tangent line is. And then x plus h is my x-coordinate, and then f of x plus h would be the y-coordinate. So those are the 2 points. And so then again, if I wanted the slope of the tangent line, I could just do y2 minus y1 over x2 minus x1, and I could find the slope. So f of x plus h minus f of x over x plus h minus x. Or if you simplified that, the x's on the bottom would cancel out, and the slope of the secant line would just be f of x plus h minus f of x all over h. Okay? And that would give me the slope of the secant line. If I wanted to use this now to get the slope of the tangent line, I want to move this, again, this second point, I want to move it closer to the first point. So I would shrink that distance h, right? I have a big old long distance between x and x plus h, but if I made that closer, if I took the slope of the tangent line now would be, if I took the limit as h approached 0, as that distance approached 0 of this slope, that would then give me the slope of the tangent line. So this is another definition we have for the slope of a tangent line. So adding to our things we had before here, the average rate of change again is the slope of the secant line. You could say it's f of x minus f of a over x minus a, depending how you define those 2 points. Or you could say it's f of x plus h minus f of x all over h, again using the definition, the second definition. Okay? Our instantaneous rate of change is the slope of the tangent line. And again, that can be defined either as the limit as x approaches a of f of x minus f of a over x minus a, or the limit as h approaches 0 of f of x plus h minus f of x all over h. Again, just depending on the definition we're using. Okay, I'm going to say of these definitions, this is the one that you're going to see more often, and we're going to pop that back up here in a little bit. But let's try to use these definitions to find the slope of the tangent line. Okay, so here we're given an equation, f of x equals x squared minus 5, and a point 3, 4, and we're going to want to try to find the slope of the tangent line using that first definition. The limit as x approaches a of f of x minus f of a all over x minus a. All right, so if we're going to do this, we want to keep in mind if I'm going to find the slope of the tangent line, with this first definition, a was the point of tangency, right? If we go back in the video, if we go back and think about look at our notes here. So I'm going to do the limit as x approaches 3 is my x-coordinate for the point of tangency. Of f of x, well, f of x is x squared minus 5 minus f of a. F of a is, I'm going to plug the 3 in. Again, a is that point of tangency. So 3 squared minus 9. F of 3 is 9 minus 5, so f of 3 is 4. Oh, duh. That's part of the point, right? So minus 4. I guess I didn't have to go figure that out. All over x minus 3. And so now I'm just going to go and evaluate this limit. Okay, so this is, I'm going to have to simplify it looks like here a little bit. The limit as x approaches 3 of x squared minus 9 over x minus 3. Which I plug in first, we're going to get 0 over 0. But I can factor x plus 3, x minus 3. And I can kill off the x minus 3's. So this becomes the limit as x approaches 3 of x plus 3, where we get 6. So the slope of the tangent line has to be 6. Okay. Once we have the slope of the tangent line, another thing we're going to have to do is we'll have to write the equation of the tangent line. In order to write the equation of the tangent line, all you need is the slope, which we just found, and a point, and I would just use point slope form. Y minus y1 equals m times x minus x1. And I would stop, oh geez. Sorry about that there. I guess I wrote too close to the border, but got out of back now. I would leave this thing in point slope form, unless you need to put it another way to match an answer, maybe in the back of the book, maybe they have it in slope intercept. But otherwise, remember, we want to stop in point slope form. That's the easiest way to do it. Okay, here's going to be another example now using the second definition. Okay, now using our second definition, the limit as h approaches 0 of f of x plus h minus f of x all over h. Again, I would say this is the one you really want to know. This is the one you will see most often. If I'm going to do it here, again, remember x in this definition was the point of tangency. So this is my x here, and this is my f of x. All right? So, f of x plus h, I'm going to go and find the limit as h approaches 0 of f of 1 plus h minus f of x. F of x, we just said, is -1 all over h. So now I've actually got to go and plug 1 plus h into my function. So this is 3 times 1 plus h squared minus 4 times 1 plus h. There's my f of h minus my f of x is -1 all over h. And I need to go and simplify this. Okay, so simplify it out. I get 3h squared plus 6h plus 3 minus 4 minus 4h plus 1 all over h. And if I simplify that some more, I get 3h squared plus 2h all over h. If I factor out an h, running out of room here, I get the limit as h approaches 0 of h times 3h plus 2, no h, all over h. And now those can cancel off. And so really if the limit as h approaches 0 of 3h plus 2, or that gives me the slope of my tangent line is 2. All right? And then again, once I get the slope of the tangent line, I can write the equation of the tangent line. So in this case, that'd be y minus -1 equals m times x minus 1. All right? And there we go. We can just leave it like that. Okay, so those were 2 examples of the definitions being put into use. But the main thing we're going to pull away from this right now is that the derivative is the slope of the tangent line, and it is the instantaneous rate of change, okay? You want those 3 things to be synonymous in your head. Derivative is the slope of the tangent line, which is also the instantaneous rate of change. I can refer to these 3 things by any of those 3 names, so know that. So our formal definition of derivative then are those definitions that we were just talking about for the slope of the tangent line. The limit as h approaches 0 of f of x plus h minus f of x over h is the most common one you will see. Okay? You might also see that the limit as x approaches c of f of x minus f of c over x minus c. That's that a1 we were talking about. Just the a has been changed to a c. You'll see sometimes either letter. That's why I changed it up. Or you might see the limit as delta x approaches 0 of f of delta x x plus delta x minus f of x over delta x. This is the same as the very top one. Instead of h is O, they use delta x's, since we're talking about that change in x, on the x-axis. So these are our 3 definitions of derivatives. Oh, and I forgot to mention, if you know that derivative is the slope of the tangent line, and I guess you've been using other things in physics to find the derivative, not this limit definition. You really need, on this unit section, I want you to use the limit definition to find all your derivatives, please. Okay? Don't cheat yet. But everything we do with derivative boils back to this limit definition. You can justify everything through this limit. That's why we started with limits. All right. Here are some quick different derivative notations that we use. The first one is f prime of x. It has like that little, I don't know, what do you call that English mark there, little apostrophe, I guess. F prime of x. We also say dy dx, okay, or the derivative of y with respect to x. That kind of goes from our delta y over delta x, since we're really talking about slope. Okay, derivative is just the slope of the tangent line. We've got y prime, and we've got the derivative of f of x with respect to x. All right, boys and girls, that pretty much wraps up today. Hope you enjoyed it. See you again real soon.